Last time you started with chemical kinetics, all of you all, right? Done very many things in chemistry till date, right from the beginning of science that you started studying. Till date, we've already done a lot. So let's start discussing. You tell me which branch of science talks about the feasibility of a reaction. So that is your thermodynamics. What talks about the extent of reaction? See, now here, thermodynamics you know deals with the heat changes, Gibbs free energy change. You know there are two parameters which talk about the feasibility. One of the parameters is your delta G, which if negative leads to a spontaneous reaction. If you have delta G as positive, then it's a non-spontaneous reaction. Again you had another parameter, that was your delta S, right? Now delta S I told you is not sufficient to explain the spontaneity. And why is delta S not sufficient? Because it talks only about the system. So you have to talk about delta S total. And then you can say that how is your delta G related to delta S? Your delta G then will be related to delta S total as delta G is equal to minus T delta S total. What you have done in your 11th grade. Then for the extent of the reaction, you have done chemical equilibrium. You remember? Because if the rate of forward reaction is much higher than the rate of the backward reaction, then in that case you expect the reaction to just proceed in a normal way as a chemical reaction, and you can even predict the extent to which the reaction is going to proceed. Tell me the name of the principle. There's only one principle that you've done in chemical kinetics, and that is your Le-Chatelier's principle. Not discussing that. Then last time you did something which helps you in determining the rate of the reaction, and that is your chemical kinetics, right? It deals with the rate of the reaction, in which all that you have done in the last two classes, I'll just quickly discuss. You have done rate of the reaction, the general rate. In fact, you can talk about two rates. One is an average rate and the other is the instantaneous rate. The only difference is average rate talks about times which are like easily you can calculate. Instantaneous rate deals with your differential equations, like you have say for example, if AA plus BB giving you CC plus DD. This is only a recap of what you've done already. So you know that average rate can be written as, for the reactants it will be minus because they are reducing over a period of time and your products are increasing. So there will be a negative sign for the reactants and a positive sign for the products. So our average will be equal to, here you will have a delta of concentration of A upon delta T, and so on for the products. I'll just put it for one of the products, that will be equal to plus 1 by C delta of C upon, and you must have done questions based on it. Then you have instantaneous rate. Your instantaneous rate is nothing but minus A. It is at any particular instant of time, so I just change it to dA by dt, and so it becomes the same for the products as well. It becomes plus 1 by C dC by dt, right? The next thing that I wanted to talk about is that related to this, before I proceed on to this, there is one law which is known as the rate law, that was given by Goldberg and Bravais. Now here rate law talks about the rate to be directly proportional to the product of the effective concentration of the reactants, each raised to the power of some term. Each raised to the power of some term. It will not necessarily be your A and B. So rate law states that your rate is directly proportional to the product of the effective concentration of each of the reactants, each raised to the power of some term. This is something that you get to know only through experiments. So it cannot be theoretically determined. Okay, so here what you can talk about is that finally your rate turns out to be equal to K into A to the power X and B to the power Y. From here, you talk about a term which is known as order. Order of the reaction is the sum of the powers in your rate law equation. This is also known as your rate law equation. This rate is the same as this rate. Okay? And then this will be equal to your expression that is given by the rate law. So you have rate to be equal to K, which is your rate constant. Remember that your rate constant is dependent upon the temperature. All physical parameters are dependent on temperature. So you have X plus Y, that will give you the order of the reaction. So therefore, if this is an experimentally determined expression, so your order also becomes an experimentally determined value. So whatever your order is, it will be an experimental determination. And it can be fractional also, and sometimes you can talk about zero order reactions also and negative also. But one term that generally students do confuse up with is that order and molecularity are absolutely different from each other. Because remember, in simple terms, what is your molecularity? It is the number of atoms, molecules, radicals or ions which are taking part in an elementary step in a reaction. So remember that order is the sum of the powers of the terms in the rate law equation, whereas your molecularity is the total number of atoms, molecules, radicals or ions. So there is no bias. Even if your radicals are reacting in an elementary step, say for example you have Cl free radical plus a Cl free radical, and if I say this is an elementary step, I will say that the molecularity is 2. So remember that molecularity is nothing but it is the total number of atoms, molecules, radicals or ions which are taking part in an elementary step, and you know elementary reactions are the ones which take place in a single step. Okay? Here molecularity cannot be negative because you are talking about molecules interacting with one another. And of course, we've already studied previously that whenever you talk of molecules, they are hard spheres. So you cannot break them into half. A molecule is a molecule. So it cannot be fractional, and negative to bilkul it's like out of bound that you talk about a negative molecularity. Iska matlab molecules react nahi kar rahe, because we are counting the numbers. And those numbers can be counted. If I tell you this is an elementary reaction, you can easily tell the molecularity. So that means ये तो आप देखते ही बता रहे हो. So this is not an experimentally determined thing. You can talk about it theoretically also. So while this is an experimental concept, this is a theoretical concept. Alright, so molecularity can be 1, 2, 3, but generally not more than 3, because the collisions which lead to effective product formation is what decides कि जितने molecules react कर रहे हैं उतनी ही molecularity होगी. And normally we've done this before, that when you actually consider any gaseous substance also, you know that there will be effective collisions between molecules. If there will be effective collisions, the chances of collisions between 2 molecules will be greater than the chances of collision between 3 at the same time. So that probability reduces on going to higher number of molecules colliding at the same time to yield a product. So molecularity is generally not greater than 3. So you can have molecularity 0 molecules reacting, matlab kuch form ही नहीं होगा, तो molecularity is never 0, it is never negative, it is never fractional. So one difference is the definition, and the other difference is coming from your basic knowledge. Yes, if you know that it is an elementary reaction. See, if you're going to have a decomposition of any molecule, you know that one molecule will definitely be present to get decomposed. So in that case, you can say that the molecularity is 1 when you balance it out. If you have half a molecule, you will not say that the molecularity is half. You will have to get the proper stoichiometry so that you can say that the molecule, because you cannot break a molecule into half, right? So it will always exist. It is only to understand the total stoichiometry when you actually put down an equation that you get those halves in order to avoid any kind of confusion. Then I think you must have done zero order reactions. Alright, Now zero order reactions means that your rate is equal to K. Now let us, because you must have arrived at some expressions in the past 2 classes for kinetics. Here remember that we take up a simple reaction, that is A is giving products. Now here I am just taking up a simple reaction where a simple molecule A is giving me products. In order to understand the expressions that we normally arrive at this level. Zero order reaction would mean rate is equal to K into A to the power 0. So here one thing is that remember that zero order reactions are alright, fine, you understand, and then there is an expression. You know that rate in this case will be equal to minus D concentration of A upon dt, that will be equal to K. So when you get K to the other side, it's very simple, so I am just taking it up quickly. dA will be equal to K into dt, and you integrate it, concentration maybe from R0 or A0 to 80, whatever you prefer, that will be A0 to 80, and from 0 to say time t. So here you know that your basic expression that you will get will be your A0 minus AT is equal to K into T, right? This is your basic expression. This will be AT minus A0, I'm sorry. It will be AT minus A0, and then you have a minus sign, so that will be equal to minus KT, or the way you're comfortable with it. Just understand the plots, because you get many plots based on it. Now here there is another concept of half-life time. One thing is, the questions which are normally asked for the entrance examinations are, what are the units of the rate constant? Now here the units of the rate constant will be, there is a general expression that you must have done, that is mole per liter 1 to the power 1 minus n second inverse. Now for a zero order reaction, anyways the concentration units are moles per liter and your time is seconds, is in seconds or minutes, the way you're recording your data. So you have moles per liter per second. So the units of rate constant in zero order fits in with this formula also. You will have 1 minus 0. So the rate constant units will be mole per liter per second. Then comes the concept of half-life time. That is the time in which the concentration of the reactant is reduced to its half. So that means your AT becomes A0 by 2. So that becomes equal to, that straight away it's equal to, यहाँ पे it will be half A2 by 2 minus, so that will be minus half, that becomes plus half. So you have T half to be equal to K by T half will be equal to, you will have here, you will have say A0 upon 2K or R0 upon 2K. So here you see R0, if you take the reactant to be R, because generally in your books it's generally referred as R, in some of the books it refers to as A. So you have that the dependence of half-life time is directly proportional to your initial concentration of the reactant. So that is what is to be remembered. Remember that here your half-life time is directly proportional. So that means your half-life time is dependent upon the initial concentration of the reactant. Then what is more important is that you remember some of the examples of zero order reactions. One example is you have all the enzyme catalyzed reactions to be, many enzyme catalyzed reactions to be of zero order. And decomposition of ammonia on a solid surface. On some solid surface of platinum, maybe nickel also is possible. So you can have the decomposition of, these are the examples which are given in your book only. So you should remember the examples as well. The decomposition of ammonia follows dash order. So you will have to check up an order. So that is a zero order. And remember, enzyme catalyzed reactions are also zero order reactions. Alright. Then thereafter, you start with the first order reactions. This is all you have done for the zero order. Then you do for the, then you start up for the first order reactions. Again, for the first order reaction, I will not be deriving it. You know how to do it. We take any, say, simple reactant giving products or R giving P. So here the general reaction will be minus of dr by dt, that is your instantaneous rate, will be equal to the rate law expression. What is your rate law expression? That is equal to k into r to the power 1. Right? So you have minus dr by dt is equal to k into r to the power 1. Now here, say I am directly coming to the expression that you get for k, that is 2.303 upon t log of r naught upon r naught upon rt. Where did this 2 come from, dear? Then when you talk about half-life, we have just started with the first law, just a revision. So you know that here k will be equal to 2.303 upon t log of r naught by rt. Otherwise, generally what you get initially is like k is equal to 1 by t ln of r naught upon rt, and here you also get it that you have your r naught to be equal to rt into e to the power of kt. Or if I take, that can also be taken, if I take RT to be equal to R naught e to the power of minus KT. This is known as your Wilhelm's equation. This is known as your Wilhelm's equation. We'll talk about it because you have not done the effective temperature, for which I'm like quickly revising this so that we can start up with whatever is left over in kinetics. So here you have this, I'm just revising the basic formulae. So here you have k is equal to 2.303 upon t log of r naught upon rt. Please remember this expression very well. Alright, and then here if I talk, now here remember that all the radioactive processes, they follow the first order reaction. All natural or artificial radioactive decay processes, because you get questions from nuclear chemistry also which are dependent on your first order only. So any kind of radioactive reaction that you get, that will follow your first order kinetics only, and from there you can easily calculate the half-life also. This is the easiest and the most commonly asked upon k. And how do you get it? You know half-life time is the time when your RT becomes equal to R naught by 2, because initial concentration ka half ho jayega. So RT is equal to R naught by 2. So you have 2.303 upon T log of R naught cancel ho jata hai, 2 comes to the numerator, log 2 is 0.3010. So when you multiply it with your 2.303, what you get is 0.693 upon K. So in brief, I just wanted you to revise the basic formula for the first order, which is important. K is equal to 2.303 upon T. All of you all repeat it once. It is 2.303 upon T log of. Very good. And then your T half is equal to 0.693 upon K. This is really important because you may be asked to find out the half-life of n number of radioactive processes, and very commonly asked in your entrance examinations also. So that is 0.693 upon K. Now there are some reactions. First order is like easily understandable. You must have derived it also and you know how to do it. But there are some reactions in which you have more than one reactants, but the rate depends only on one of the reactants. Like for example, if I say that my A plus B is giving me say product C plus D or whatever. So here my rate expression, what you assume is that it can be K into A to the power some term X and to the P into B to the power Y. Both are like, so your rate should be dependent on both of the reactants. Now sometimes it may so happen that the dependence on, if I take B in large amount, alright, if I take B in large amount, then during the course of the reaction the concentration of B will remain unaltered. Like say for example, if I am carrying out some reaction in water, and if I take water in large excess, then towards the end it is experimentally observed. मैं बता रही हूँ कि अगर पानी बहुत एक्सेस में ले लेंगे तो टुवर्ड्स द एंड ऑफ द रिएक्शन वील सी दैट ड्यूरिंग द कोर्स ऑफ द रिएक्शन जो वाटर की कॉन्सेंट्रेशन है दैट रिमेन्ड अनऑल्टर्ड. तो इसका मतलब ये वाली जो कॉन्सेंट्रेशन है, से इफ B is your water, this concentration almost remains as a constant. You getting the point? If I take one of the reactants in excess, then the concentration of that reactant will almost remain constant throughout. So because of that, we get K dash as the new rate constant, because rate constant is a constant for a particular reaction at a particular temperature. So then we get a new rate constant K dash, which is equal to K into the concentration of the excess of the reactant, such that your rate is now dependent only on one of the reactants, and generally the order of the reaction that I am talking about is 1. So then in that case you call those reactions as pseudo first order reactions. You call them, then let me tell you, pseudo first order reaction means that your rate is equal to K dash to the power K dash into A to the power 1. So the rest of the formulae for the pseudo first order reaction remains the same. K will be equal to T upon 2.303 upon T log of R naught by RT. So the rest and T half will also remain the same, that is 0.693 upon K. So that will just remain the same. All you need to remember is that here, say in pseudo first order reaction, you have the dependence of the rate only on one of the reactants. So pseudo first order reactions are such which have more than one reactants, but your concentration is just, your rate is dependent only on one of the reactants. One of the best examples and one of the most important reactions that you will keep doing again and again will be your acid hydrolysis of ester. Acid hydrolysis of ester. Acid means H plus, hydrolysis means we are breaking water, of ester. Now ester you've already done in 10th grade. क्या होते हैं? जैसे if I talk about methyl acetate, so it will be CH3, COO, C2H5. This is an ester. Ester are of the types RCOO R dash. ये एक group है RCOO R dash. Correct? This is an ester. You will be studying it in organic chemistry also. So this is your methyl, and this is 1, 2. This is your methyl acetate, and the IUPAC name is methyl ethanoate. Ethyl ethanoate. I'm sorry. This is your ethyl, and this is 1, 2. So you will check up this carbon also. So this will be ethyl ethanoate. Okay. So this plus water will now bring about, in the presence of acid, will now give you CH3. Now water is getting broken up, so you have lysis of water, so you have H getting added up here and OH coming here, because later on when you do organic chemistry, there you will be doing the preparation of acid from ester. तो तब भी ये reaction काम आएगी. Otherwise, what is the significance that you are doing right now? That this is a special first order reaction, which is a pseudo first order reaction. So here what you have is, this will be CH3 now COOH plus C2H5OH. However, we are not concerned with the products at the present state, because this reaction you will be doing again, so you should remember it right here. So I repeat, acid hydrolysis of ester. Please remember, acid hydrolysis of ester is a pseudo first order reaction. But if it was a base hydrolysis भी होता है ester का, उसमें भी you get the same products. But the only thing is, instead of H plus you have OH minus, and that is a second order reaction. तो ये भी याद रखना, acid hydrolysis of ester is a first order reaction, whereas base hydrolysis of ester is a second order reaction. And there the rate is dependent on ester and the base concentration, OH minus ion concentration. So the order is 1 with respect to the ester and 1 with respect to the OH minus ions. Clear? So it is very important that you remember that pseudo first order reaction is acid hydrolysis of ester. But then again we are taking water in excess. Here you have in experiment you have 3 reactants. So when we carry out the experiment, you must have also done some numerical probably last time, in which you have different concentration terms. Say you have say A, B, and you are given the rate. Alright, you will be given the concentration C1, C2, then C1, C3, and then C4 and C2. ऐसे numericals आते हैं. So what you have is, and you are given the rate 1, rate 2, rate 3. So 3 reactions का आपके पास data है. तो ऐसे ही हम क्या करते हैं, जब 3 reactants हैं, we consider water as 1, we consider acid as 1, and we consider ester as 1. फिर हमारे पास एक C भी आ जाता है, and then we find out the order with respect to each of the reactants. So this is again order is an experimentally determined. जब तक आपके पास ये data नहीं होगा, आप कैसे बोलोगे कि order क्या है? This is how you find out the order. ये वाला numerical ऐसा सबने क्या होगा? It's given also in your book. What you have to do is R1 by R3 करोगे, तो you will get K1 by K3. Your C1 and C1 will get cancelled. So that means your A terms goes off, and you have C2 by C3 to the power Y. If in this case rate is equal to K, reactants की concentration given है, so that will be A to the power X and B to the power Y. तो पहले we'll choose those reactions in which one of the two concentrations are same, so that they cancel off. So we choose R1 by R2. So R1 by R2 जब करेंगे, so we get K1 by, or sorry, we're just finding out. Rate constant will be the constant for a particular reaction, I'm sorry. So in that case your A term and the A term will get cancelled off because the concentration is the same. So that goes off, and then you will have C2 by C3 to the power Y. And you check up the relationship between these two and you get the value of Y. And then you can easily calculate the value of X. And once you know the value of X and Y, ये हमें पता है, किसी भी फिर एक रिएक्शन को पिकअप कर लो. दिस इज द जनरल स्ट्रैटेजी. किसी भी एक रिएक्शन को पिकअप कर लो, A की कॉन्सेंट्रेशन डालो C1, X निकाल चुके होगे, ठीक है. B की कॉन्सेंट्रेशन विल बी C2, Y is again determined before, so you know the rate for that particular reaction, then you can calculate the rate constant. So these type of numericals are very common. So what I am telling you is like, it is like an experimentally determined expression and quantity order, so you cannot predict it otherwise. So just by looking at it, you cannot say that the order may be 1 with respect to any of these, unless and until you have an experimental validation. So here you have that the acidic hydrolysis of ester is a pseudo first order reaction. और pseudo क्यों डाला हमने? Because you have more than one reactants, but the rate depends on only one, and the order with respect to that reactant is 1. Another very important example is inversion of cane sugar, that is C12. Cane sugar is your C12H22O11 plus water. Inversion of cane sugar will give you nothing but that will be C6, that will be C6H12O6, and again you will have C6H12O6, and that is also in the presence of acid. If I say this is not an elementary reaction, you cannot predict the molecularity unless and until you are very sure that your reaction is an elementary reaction. Elementary reaction क्या होती है? जो भी single step reaction है, अगर उसके लिए कई you have different pathways, which is possible in this case, that an H attacking first and an OH minus attacking later, कई reactions होती हैं. There are two types of reactions. One is an elementary reaction and the other is a complex reaction. Elementary reaction एक ही step में होगी, complex will be in multiple steps. So you have to actually, and for multiple steps when you have, वो एक एक स्टेप का आप बता सकते हो कि मॉलिक्यूलैरिटी क्या होगा, ठीक है ना. व्हाई इज दिस कॉल्ड इन्वर्जन ऑफ केन शुगर? Step. In the complex reaction, the rate depends on the slowest step. That is called your rate determining step. And you find out the order from that particular step only. And your rate law expression is also written from your slowest step. Generally, it is dependent on the slowest step. Alright. Now we come back to the inversion of cane sugar. This is your cane sugar, this is your glucose, and this is your fructose. Let me tell you, why is this called inversion of cane sugar? क्योंकि हमारा जो केन शुगर होता है दैट इज जनरली डेक्स्ट्रोरोटेटरी एंड योर ग्लूकोज इज डेक्स्ट्रोरोटेटरी. नाउ व्हाट इज दिस? मेनी ऑफ यू कैरी अ क्वेश्चन मार्क. हमारी एक प्लेन पोलराइज लाइट होती है दैट यू स्टडीड इन फिजिक्स. व्हेन आई प्लेस अ ग्लूकोज क्रिस्टल या कोई भी क्रिस्टल अगर मैं उसके सामने रख रही हूँ तो वो उस प्लेन पोलराइज लाइट को आइदर राइट की तरफ रोटेट कर देगा या फिर लेफ्ट की तरफ. अगर वो राइट की तरफ, ये भी ऐसे ही देखते ही नहीं बता सकते. दिस इज अगेन यू विल हैव टू डू इट एक्सपेरिमेंटली. सो अगर वो राइट की तरफ रोटेट कर रहा है देन इट इज डेक्स्ट्रो रोटेटरी. अगर वो लेफ्ट की तरफ रोटेट कर रहा है तो देन इट इज लीवो रोटेटरी. नाउ व्हाट हैपेंस इन दिस केस? दिस इज डेक्स्ट्रो रोटेटरी. Plane polarized light, the light which travels only in one particular direction. So then you have a crystal placed. उस crystal से जब light pass हो जाती है ना इस side को, so either it turns the plane polarized light towards the right or it changes its direction towards the left. If it changes towards the right, it's dextro, and if it changes towards left, तो ये उस crystal की property है जो बीच में हमने रखा है, ठीक है. So now here, if you have inversion of cane sugar, तो cane sugar is dextrorotatory. Now this is dextro and this is levo. होता क्या है, levo और dextro की एक वैल्यू होती है कितने डिग्री से चेंज किया. तो इसके अंदर the overall reaction turns out to be the final is like levo. तो क्या होता है, रोटेशन पहले अगर राइट की तरफ थी तो बाद में क्या हो जाएगी, लेफ्ट की तरफ. तो इसीलिए कहते हैं इट इज कॉल्ड इन्वर्जन ऑफ केन शुगर. एंड अगेन रिमेंबर दैट दिस इज अ pseudo first order reaction. Done? So with this we complete the first order reaction. Given you the example of a second order reaction. Yes. Molecularity and order are same in the elementary reaction. That depends upon the, no, again you will have to find out the order, so you cannot say it theoretically. Order is just not at all a theoretical concept. It is purely an experimental concept. So for zero order reaction, yes, because then you will not have any dependence on the rate the initial concentration only. So then also in that case you can say. But still, it's always better to make sure that the order is experimentally determined. So unless and until you're told that the order of a particular reaction is this, because earlier it was believed. And in fact, when I was studied the first order reaction, pseudo first order reaction for the first time, let me tell you, there was another name that was earlier given on to it, that was pseudo unimolecular reaction. So instead of depending on 2 or 3 molecules, it depended only on 1 molecule. So that designation was later withdrawn and now it is only called as pseudo first order reactions. Alright, so then you have, yes, because any reaction can happen in a single step. So if you have any reaction which is happening in a single step, that's an elementary reaction. But again, for all these data, you need to do the reactions and then find it out. So to find out, but elementary reactions and complex reactions and order and rate law, all these are determined from your experiments only when you have the data with you. Okay, now next we come on to the effect of temperature. Effect of temperature on the rate of the reaction. Remember that when we increase the temperature, तो क्या होता है, kinetic energy बढ़ जाती है. अगर if the kinetic energy increases, then your collision frequency will increase or collision will increase. If collisions will increase, then the rate will become faster. Now just remember this, a question which is normally asked, for every 10 degrees, this is given also in all the books, for every 10 degrees rise in temperature, you will have the rate of the reaction getting almost doubled. Okay? And generally the temperature coefficient is, that is why known as the rate constant that you measure at T plus 10 to the rate constant that you measure at T. So this ratio is sometimes known as the temperature coefficient. Otherwise, remember that the rate of the reaction generally increases on increasing the temperature. And it is found that for almost all the reactions, for every 10 degrees rise in temperature, the rate of the reaction is nearly doubled. And this dependence is also shown from the Arrhenius equation, which somebody asked as a doubt. The Arrhenius equation is, you have the rate constant K. The rate constant, now you all are familiar with the rate constant and the units for a 0, first, second, nth order reaction. So you have K to be equal to A e to the power of minus EA by RT. This is A. A is a subscript to E. So this is your active. Now this is your either the frequency factor or the Arrhenius constant or the pre-exponential factor. So you can have different names for this A. This is the Arrhenius equation. It is given by Arrhenius. Alright. Then this is also known as the Arrhenius constant or the pre-exponential factor or the frequency factor. Now here, what you need to understand is that this activation energy is the minimum energy which is required for your reactants. Like for example, let me just talk about this graph that is generally drawn, the potential energy curve, or it is also known as the reaction profile. I represent my reaction coordinates here, reaction coordinates. Now I have my reactants A plus B. उनके पास अपनी कोई एनर्जी है. Now the minimum energy that is required for the reactants to cross over this energy barrier, क्योंकि एक barrier होता है, यहाँ पे एक intermediate complex form होता है. So this is the energy that corresponds to your intermediate some kind of a complex which may be hypothetical. वो बनता है, उसके बाद then your products are formed which generally lie at a lower energy. So what happens here? You have a reaction A plus B is giving you C plus D. तो reactants की जो generally energy होती है, उसको एक minimum energy चाहिए to cross over this energy barrier. Some minimum energy is required to cross this energy barrier to reach the state of the products. This energy or this threshold energy is your activation energy. So activation energy is the minimum energy required by the reactants to cross over the energy barrier to form products. If this is less than EA, then your products will not get formed. Like for example, the general example which is cited is H2 plus I2, that's giving HI, 2HI. होता क्या है? Your H2 and I2 are your A and B. So it will form some kind of a complex, like you have H2. Ab HH will get broken up definitely. You will have I and I2 will also get broken up, and you will have some kind of a complex, intermediate complex which is formed. इस complex की energy is high, क्योंकि जो भी चीज़ unstable होगी ना, उसकी energy हमेशा high ही होगी. ठीक है? So if you have some kind of a complex which is unstable, definitely that will be lying at a higher energy. Remember, instability is always related to higher energy. और जितनी कम energy होगी उतनी ज़्यादा stability होगी. So that is why, otherwise what is the need for the reactants to undergo a particular reaction to form products? So here this is some kind of a complex which is formed, which is at a higher energy level, and once the energy reaches this activated complex part, then it simply breaks down to form your products, which is like 2HI in this case. Got it? So this is your basic theory behind the Arrhenius equation. So then we also have to start off with solid state. Please remember that.
If in every reaction this complex is formed, we cannot call any reaction to be elementary or simple.
See, See, it is, that is why I said it's kind of a hypothetical concept also. Because if a reaction is taking part in a single step, I will take up that example also. You have to do collision theory also after this. In that I will take up an example in which you will understand it is not only the simple reactants which are reacting with one another, but also the orientation in which it is important. So if your molecules are oriented in such a way, they will quickly form that intermediate complex and lead to the formation. So that's a one step. अगर आपका कोई इंटरमीडिएट कॉम्प्लेक्स बन रहा है तो वो अनस्टेबल है, उसको हम मानते ही नहीं है, बिकॉज एनी स्पीशीज विच इज एक्सट्रीमली शॉर्ट लिव्ड, कोई भी अगर एक स्पीशीज जो बहुत बहुत टाइनी पीरियड के लिए इज देयर, that is not considered to be a particular part, because you need some kind of a stability or stable lifetime for a product to exist. If you cannot actually have it, then isolate it or have it in general for any kind of an application, then that is not considered. So in this is formed and then quickly it reaches your products. Fine. Threshold energy is the minimum energy. Threshold energy, you remember हमने threshold का word पहले कहाँ use करा, photo electric effect में. कुछ एक मिनिमम एनर्जी चाहिए, अगर उस मिनिमम एनर्जी तक नहीं पहुंचे तो देन योर रिएक्शन विल नॉट अकर. सो थ्रेशोल्ड एनर्जी इज सम काइंड ऑफ अ मिनिमम एनर्जी व्हिच इज रिक्वायर्ड फॉर योर प्रोडक्ट्स टू गेट फॉर्म्ड. और थ्रेशोल्ड एनर्जी, इन दिस केस द थ्रेशोल्ड एनर्जी इज इक्वल टू द एक्टिवेशन एनर्जी, राइट. यहाँ पे आर्हीनियस के टर्म्स में योर एक्टिवेशन एनर्जी इज द मिनिमम एनर्जी व्हिच इज रिक्वायर्ड. So that is an analogous term to your threshold energy. क्योंकि कोई और theory देगा तो he won't use this activation energy concept, probably he'll call it threshold energy. Getting? They're similar, yes? Here you can say it's same, but because I am talking in context with your Arrhenius equation, so here the minimum energy I am calling it the activation energy. Otherwise you can say that threshold energy is similar to your activation energy because that's the minimum energy which is required. So this is the threshold energy barrier. अगर मैं किसी और reaction profile की generally बात करूँ, we call it the threshold energy barrier or activation energy. So it's just the same. EA is equal to TE. Now we are entering into the concept of thermodynamics now. If you're talking about the internal energy, every state, every system possesses some internal energy which is stored in it, which is equal to Q plus W. So वो तो है ही. अगर वो internal energy नहीं होती तो फिर it would not have actually used up that kinetic energy to cross over the energy barrier. So the system has some energy already and then it attains a more stable energy which is lower than the previous energy. Okay? Clear? Now, Arrhenius equation is K is equal to, please remember the Arrhenius equation, K is equal to A e to the power of minus EA by RT. Terms are qualified, you remember each of the terms. R is your rate constant, not the initials of my name. T is also not the initial of my name. T is your temperature. So R and T stand for your universal gas constant and your temperature. Now here, एक और चीज समझो which is very much evident because mathematically also it is proved. अगर temperature बढ़ जाएगा तो this EA upon RT term, A is a subscript only, EA upon RT term will be reduced because temperature denominator में है. So if this reduces then your minus term will increase. So as a result, your minus term will then decrease because this term is decreasing. So your power term, which is a minus factor, will also decrease, and if that will decrease then your minus, exponential is to the power minus, so your rate constant will increase. Got the point? So it is also directly related to that. Alright, so now here you can also take the natural log, you get numericals based on it. The natural log will yield ln of k is equal to ln of A minus EA upon RT. ln of k is equal to ln of A minus EA upon RT. Now here you can also have a graph between ln k. ग्राफ्स तो बहुत सारे बनते हैं, जैसे फर्स्ट ऑर्डर में भी बनाए होंगे. ln k और 1/t में अगर मैं ग्राफ बनाऊं, सो दिस इज योर y, ठीक है, ln k मेरा y हो गया, योर 1/t is your x. So if I take it to be y is equal to mx plus c, if I take it to be like that, y is equal, it should be a straight line, but the slope Slope is m, which is minus EA by R. So it will be a straight line with a negative slope. I repeat, you know the straight line graphs. It is simply a y is equal to mx plus c graph. X क्या है हमारा 1 by t. Y क्या है ln k. Just look at it, look at the equation you can form. Now from here you can easily say that the intercept, that is c, will be equal to your ln a. तो इसको बैक एक्सट्रापोलेट करेंगे तो योर ln k वैल्यू जो भी यहाँ पे होगी that is equal to your ln a. And your slope, you know how to find out the slope? So y2 minus y1 upon x2 minus. So what you have, the slope here will be then equal to minus EA by R. Okay? All of you all know this. Nothing that special that we've done. Okay, hurry up so that at least the concept gets over. Arrhenius equation, remember it in your minds quickly. K is equal to A e to the power of minus EA by RT. Remember the natural logarithm expression also, ln k is equal to, that you can easily arrive at also. ln k is equal to ln A minus EA by RT. अगर इसका natural log लेंगे, so then you will have a term, you will have log k is equal to say ln A, sorry, log A minus EA upon 2.303 RT, right? Your log to the base 10 will become log k is equal to log A minus E upon 2.303 RT. Now if I talk about two reactions, then I will be talking about say K1. अगर एक रिएक्शन लूँ मैं जिसका रेट कांस्टेंट इज K1 and it is carried out at say another temperature say T1, then in that case I can easily take up the ratio and find out the other rate constant, because if this is for one of the reactions, how can this reaction be used? Arrhenius reaction हमने लिखा in terms of log as log K1. K1 is the rate constant of reaction number 1 and that is carried out at temperature T1. Similarly for a reaction 2, your reaction 2 which is carried out at a different temperature, or you know K is dependent on temperature, so it can be for the same reaction also, log K2 will be equal to log of A minus EA upon, please remember that A here everywhere is a subscript, so EA is your activation energy, so 2.303 RT2. So you can take the ratio of the two and can easily find out. Oh, sorry, you take the difference of the two expressions. So you will have log K1 minus log K2, log A cancel. You will have minus of E upon 2.303 R into 1 by T1 minus 1 by T2. Is that clear? So just please remember this expression for numericals, that log of K2 by K1 is equal to EA upon 2.303 R into 1 by T1 minus 1 by T2. Please check this once quickly. If I have not taken minus outside, K2 by K1 I have taken. So it will be 1 by T2. Please check that once again. Log of K2 by K1. So right. So I take, so there will be a minus outside. So it will be minus of EA by 2.303 R into 1 by T2 minus 1 by T1. You do it and just check it out quickly. Please remember that there should be no discrepancy with this. And this can be done in terms of ln also. You just have to remove 2.303. If it is in natural log terms, you accepted. So remember log of K2 by K1 is equal to EA upon 2.303 R. So now this is like ready for you to remember and have. So what is this? Log of K2 by K1 is equal to EA upon 2.303 R. Learnt? Very good. All of you all? So this is nothing but this is also T1 T2 upon, sorry, this will be T2 minus T1 upon T2 T1. So log of, so this is also another form in which it is given sometimes in the expressions of MCQs, that this is equal to now T2 minus T1 upon T1 T2. Okay? So these are the various forms of your Arrhenius equation that you can remember. Then what is the effect of catalyst on a chemical reaction? Effect of temperature is done. So remember that catalyst is the one which increases the rate of the reaction. If it reduces the rate of the reaction, generally you do not call it a catalyst, you call it an inhibitor. So inhibitor is the one which reduces the rate of the reaction, and catalyst is the one which increases the rate of the reaction. So in this case, catalyst is the one which increases the rate of the reaction. How does it increase the rate of the reaction? If this is a normal reaction profile, what it does is it reduces the activation energy. So catalyst does its work by increasing the rate of the reaction by decreasing the activation energy. And this is a part of your intermediate complex theory. This concept of explanation, this is your normal reaction profile. Remember that if you have to draw a graph in some subjective paper, do not leave your axis blank ever, because that axis can stand for anything. So you should always be mentioning that here you are representing your potential energy and here these are your reaction coordinates. Yes. No. But it will still need to get formed. इसमें क्या होगा? Activation energy अगर कम हो गई तो वो फिर you are supplying now catalyst. What is a catalyst? Catalyst is related to your surface chemistry again you will be studying. Catalyst सिर्फ एक surface provide करता है. It provides a surface on which the reaction can occur. Say my this palm is like a catalyst. What will reactants do? They will come, sit on the vacant sites, carry out the reaction, and then just get cleave from the surface. So catalyst has no role to play absolutely in the reaction. So that is why whenever you find or write down the rate law equation, catalysts are never a part of it. One thing is that. The second thing is that when you are talking about the effect of catalyst, how does it increase the rate? Because kinetics mein to it's all related to rate. If it is not participating in the reaction, how does it increase the rate? Because now it is providing a surface where the complex will quickly get formed. So energy कम हो गई. पहले the reactants as in case of H2 and I2 would have looked for an appropriate site. जब तक catalyst नहीं है उन्हें कोई जगह चाहिए जहाँ पे वो complex form करेंगे. So they will be wasting energy, using that energy in finding that site. Form the complex, then form the products. इस case में क्या करा catalyst ने? It provided a surface कि come here, carry out your reaction and then just go. So it reduces the activation. तो उतनी energy बच गई ना. So it reduces the activation energy and then increases the rate of the reaction. Clear? So remember that the effect of catalyst is only this, and it is a part of intermediate complex theory. Okay. Then we have let's talk about another theory which has been proposed for the chemical reactions, and that is the collision theory, which was given by Trotz and Lewis. Okay, just if you can remember, T and L, Trotz, the names are Max Trotz and William Lewis. They had proposed this theory, and you know the theory was like something which you now understand very clearly because you've done so many chemical reactions. For any chemical reaction to take place, what is important? Collisions are important. Okay, now if collisions are important, apart from collisions, it is very important that they should be colliding at the proper frequency. That means that threshold frequency or threshold energy that we are talking about. So here, when you have to talk about, say if you are talking about A plus B is giving any products, then say the rate will now be, now you have done one expression. What was that? That was your K was equal to A e to the power of minus EA by RT. Now here Trotz and Lewis stated that your rate is directly proportional to e to the power of minus EA by RT, and simultaneously it's related to a collision frequency between A and B. Okay, now this collision frequency is similar to your Arrhenius constant, But remember, there we were talking about K, here we are talking about rate. दोनों में फर्क है. Rate is directly proportional to your rate constant always. So here what you have is rate is equal to ZAB into e to the power of minus EA by RT. What is the ZAB? It is the collision frequency. Collision frequency. What is collision frequency? The number of molecules colliding per unit time per unit volume. Okay, collision frequency is a factor which is nothing but the number of molecules which are reacting per unit time per unit volume, क्योंकि you have to consider volume also into consideration and per unit time. So that's your collision frequency ZAB. It can be considered similar to your A factor. Now apart from this, what is stated, please look up here now for an important reaction. This is all your collision theory states. Collision theory में बस एक और additional factor है. It states that not only collisions are important, but proper orientation of the molecules is also important. So that proper orientation means जब तक molecules say if I have to fit in this cap to this pen, I cannot fit it from here at all. I need this to be aligned either like this or like this. So there are two orientations possible in this case. ठीक है? So that orientation factor is also important to form the final product. Got it? So collision theory states that apart from collision frequency, the definition of which you should be knowing. What is the definition? The number of molecules colliding per unit volume per unit time. So your rate is directly proportional to collision frequency into the e to the power minus EA by RT term. And along with that you need to have proper orientation also. Now proper orientation means if I actually put my hand here, what will happen? It will repel the approach of the cap and will not allow it to come to this. So that means I will call it some kind of a steric factor, right? If I remove this, this comes in. So we can add on another factor to this expression, that is your P factor, which is also known as the steric factor. So the total expression according to collision theory for a rate becomes equal to P into ZAB into e to the power of minus EA by RT. Repeat it once for me. For collision theory, rate is equal to
P into ZAB into e to the power
minus EA by RT. Okay. So this is your rate of the reaction, which can be generally defined like that. That means in short, I'll put down the collision theory that the effective collisions should take place, and for that you need sufficient kinetic energy plus the proper orientation. I'll just take another 2-3 minutes to explain the proper orientation and then we proceed on with the next topic. Now here what you have is effective collision should take place for a reaction to proceed. So for those effective collisions, what is important is you should have sufficient kinetic energy. What do you mean by sufficient kinetic energy? It is the same. It is your threshold energy. The minimum energy which is required for the reactants to form the products. So that is your threshold energy. Threshold. Otherwise you may confuse it with thermal also. So it is threshold energy plus the proper orientation. Collision theory done. That was the last topic that you were supposed to do in kinetics. Now here I repeat, collision theory states that it is directly proportional to your frequency factor and e to the power of minus EA by RT. Now you know the temperature dependence. Temperature बढ़ेगा तो क्या होगा? You know it very well, right? Another factor which we are just introducing according to collision theory is your P, which is your steric factor. And you should remember it to express it qualitatively if you get a short note just in case in your normal examinations, that the effective collisions should take place, which means that there should be sufficient energy, kinetic energy or threshold energy. Explain threshold energy then. Threshold energy along with proper orientation of the molecules. Now in order to explain the proper orientation, I'll just take up one example and that'll be all. Yeah, here for the proper orientation, say I take up the example of nucleophilic substitution of any molecule. Say I take C2, oh no, I'll take a simpler one, CH3 CH3 Br. C की हाइब्रिडाइजेशन बताओ. sp3. 4 single bonds along C means sp3. Please do not let your mind get rusted for the examinations. Keep oiling them. Right? How do you keep oiling? By revising thoda thoda har jagah pe, because now all your concepts that you've done till now, say it be your 7th, 8th, 9th, 10th, 11th grade, everything is required. I have told you, I'm just repeating it again. Carbon along, if you have 4 single bonds around carbon, वैसे ये गलत तरीका है, but to remember, carbon along 4, if you have 4 single bonds along carbon, it is always sp3. Once double bond, sp2. One triple bond, sp. Right? I repeat, 4 single bonds along carbon, sp3. One double bond along carbon, one double bond, remember. One triple bond along carbon, it will be sp. Okay? 2 double bonds along the carbon, sp. If you have carbon, so this carbon will be sp hybridized. Please, there are many questions which are asked for the hybridization of a particular carbon number. So you can just look at it and tell whether it is sp3 hybridized, sp2 or sp. So here in this case, this one will be your sp. Okay. Now here you have, this you will be doing in organic chemistry also. This is, जब कार्बन सिर्फ एक ही और functional group को attached है, you generally call it 1 degree carbon. Alright, when in carbon is attached to just one carbon atom, this is also 1 degree. CH3, CH2, Br. This is also 1 degree. This is 1 degree carbon. 1 degree means primary. ठीक है, सिर्फ ऐसे ही सुनना. This is not related to what I'm talking about. But अगर मैंने एक हाइड्रोजन हटा दिया, अब यहाँ पे एक और CH3 बना दिया. When carbon is now attached to 2 carbon atoms, it is 2 degree. It is secondary. Now I remove this hydrogen and now one more carbon. Now this is your tertiary. Clear to everyone? ठीक है. Now this is your 1 degree. अगर यहाँ पे CH3, CH2 Br होता, that also is 1 degree when your carbon is just attached to one carbon. When your first carbon, अच्छा first carbon मतलब जो पहला carbon functional group को attached है, that's alpha. The second carbon is beta. अगर third carbon होता तो gamma. This is also beta, this is also beta. Clear with that? Right? Okay, so now here we have, I am just talking about a primary alkyl halide. Halogen है ना ये bromine? ठीक है? So now when I talk about a OH minus approach to this Br, now there are 2 kinds of approaches. Either I make it attack right directly from here, ठीक है? Or ये OH comes from the other side. Okay? Now you know that Br is negatively charged and C will be positively charged. But I have told you that don't put positive and negative unless and until the bond is broken. So delta negative, delta positive, partial. Because bromine is more electronegative in nature. Electronegative means it is a tendency to pull electron density. So this is delta negative, this is delta positive. Now if OH minus will come and approach this Br, one orientation is this, so Br will repel it. If Br will repel it, so then that means no product formation. So then in that case the proper orientation is not there, so reaction nahi hoga. But if OH minus comes and approaches from the other direction, और ये कर भी सकता है क्योंकि hydrogens are small atoms, so they will allow the approach of OH minus from the other side, and then in that case you will have इसका intermediate ऐसे बनेगा, OH will get attached to C, 3H, and you will have Br here. This is your, why am I putting this in this? Because this is like unstable intermediate, and carbon की valency वैसे भी 4 से ज़्यादा नहीं हो सकती. यहाँ I am drawing 5 groups around it. So immediately this is like an intermediate which is formed, and immediately it will form your CH3OH onto the other side. So when the proper, अगर वो orientation same side से होता, so then there is no product formation, and when the OH is coming from the other side, there will be a product formation. Now because you are doing it here, I'll just tell you that this will be called substitution nucleophilic unimolecular reaction. No, this is substitution nucleophilic bimolecular reaction, because your two reactants are taking part in the elementary step. Get it? Substitution क्यों? क्योंकि bromine निकला, OH लग गया, substitute हो गया, right? Substitution. Nucleophile क्यों? Electron rich species are nucleophiles. Electron deficient species are electrophiles. Many people learn it as electrophiles are electron loving species. ठीक है? So electrophiles are electron loving or they are electron deficient. नहीं है तभी they have the love for the electrons. So electrophiles are electron deficient and this is a nucleophile. और nucleophile क्यों है? Negative charge means इसने एक electron pair लिया हुआ है. So it already has extra electrons. I hope you remember this, the basics. जितने भी negatively charged ions होते हैं वो सारे nucleophiles होते हैं, because negative means they have taken up an electron pair. So they have extra electrons. So nucleophile. So this is called nucleophilic substitution. So substitution nucleophilic. समझ में आया? Bimolecular. Why bimolecular? Because you have one molecule which is the base and the other molecule which is your primary alkyl halide. Okay. So then this is your SN2 reaction. समझ आया? This is a mechanism कि कहाँ से अप्रोच किया है इसने ऑपोजिट साइड में. और इस केस में क्या होता है? देयर इज एन इन्वर्जन. पहले ये Br इधर था, अब OH इधर है, तो व्हाट हैपेंड टू द मॉलिक्यूल? इट गॉट इन्वर्टेड. Br पहले इधर था, अब OH इधर था, तो रिमेंबर SN2 में इन्वर्जन हो जाता है. ठीक है? रेस्ट SN1 you do it in organic whenever you do organic. All right, so we are talking about a primary halide. It should have proper orientation with your incoming nucleophile to form product which is a part of your collision theory. So this example should be remembered. And if OH minus attacks from the same side, then it will not yield. From which theory do you get to know about it? Collision theory. Okay. Now with kinetics now. So if we get time, we'll take up more questions in kinetics later. But today we were to start with solid state. All right. Yes. For a single reactant also, when you talk about a single reactant, उसका मतलब ये है कि that molecule will be colliding, because one mole of a particular atom consists of Avogadro number of atoms in itself. So whenever you talk about it, so there that molecule will be reacting with other molecules to yield your particular product. But when you talk about decomposition, that involves only one molecule, if you can talk about that. Okay. Now we start with a new topic, which is, so I'll put it in bold because it is solid state. Now we've already done gaseous state, we've studied about liquid state. So solid state is something which is everywhere around you, but here when we are talking about solids, remember there are some important factors which demarcate it from liquid and gaseous state, which you all know. One is to decide on whether it is a solid state, which are much greater than thermal energy, right? Remember that this is, what is the density for solids? It's the, in comparison to liquids and gases, density is the highest. They are the most densest out of liquid and gaseous state. What is density? Mass by volume. So then after density we can talk about compressibility. That is the least. And then the other properties that you can talk about, right? Solid state is something which we are now going to talk about. Solid state has the properties which you know, these are right from your childhood, you've been doing this, that intermolecular forces are really high, higher than what? Thermal energy, and then your density is more, maximum compressibility, and then you have other things also that you can talk about. But now let's quickly come to the classification of solids. Now depending upon the order in which the atoms are arranged in a solid, atoms or molecules are arranged in a particular solid, you can have, depending upon the order, you can have two types of solids. One is crystalline and the other is amorphous. Okay, the very first chapter probably, so you all must be absolutely thorough by now. So you have crystalline solids and amorphous solids. Okay, quickly to jot down the differences, you know that crystalline solids have a definite shape, amorphous have an irregular shape. क्योंकि crystalline, as the name suggests, it's a crystal, so you have a regular pattern of arrangement कि जो एक particular half, एक particular site पे आपने देखा, that pattern will get repeated over a long range. So that is why they are said to have a definite order, and that order is a long range order. So that is why crystalline solids are called long range ordered solids. Amorphous solids are called short range order because they have an irregular kind of a shape. They have an irregular shape. Another thing is like when you talk about crystals, when you cut your crystals, you get absolutely plain and nice surfaces. But for amorphous, you get irregular irregular surface. So then the next thing is you talk about heat of fusion. In this case, there is a definite heat of fusion. In this case, there is it does not possess any definite heat of fusion. Very important property now. That is like these are anisotropic in nature and these are isotropic in nature. Now isotropy refers to a property that talks about the property to be same along different directions. अगर कोई particular property is same along different directions, then you call it isotropy. And if it is different along different directions, then it is anisotropic. Okay. Now why are crystalline solids anisotropic in nature? Please remember, this is like very important. Many students straight away jump on to say क्योंकि सारी you have all the particular things with your crystalline solids, so it is like a temptation to say that they are isotropic in nature. But crystalline जो properly ordered होते हैं, they are anisotropic in nature. The reason being, like you have say NaCl crystal, say this is Na, this is Cl, say this is Na. All right, this is NaCl. All right, NaCl. All right. So here you have this, and then you have this NaCl. So then in that case you will have Na here, Cl here, Cl and Na, and then again, so that kind of an order will be like followed. You have Na, Cl, Na and Cl. Alright, now if you talk about any property like refractive index, kaun si property? So if you move along this direction, your property is meeting all your Cl ions, right? And if you move along this direction, now it is like Cl, NaCl, NaCl, Na and so on. So because the refractive index here is along all the Cl atoms, and in this case it's along NaCl, NaCl, so because of their ordered arrangement, the properties are different along different directions. Got it? So your crystalline solids are anisotropic in nature, whereas your amorphous solids are isotropic. Now how come amorphous? Because they're already irregular pattern, तो किसी भी pattern में जाओ, it's irregular, and the irregularity is like can be compared over when you move on to a long range to find out for the amorphous solid, or that for that short range that you have, you find that the properties are similar along different direction. So amorphous solids are isotropic in nature. Next thing that you should know actually is like another name for the crystalline solids, they are known as true solids. These are known as pseudo solids. Okay, these are the true solids and these are the pseudo solids. Okay, and then examples here you can have for crystals, you can have n number of examples. Your crystals, NaCl crystal, you can talk about quartz is a crystalline substance, but quartz glass is amorphous. Please remember this, quartz is crystalline in nature, but quartz glass is amorphous in nature. And then you have glass, they are known as supercooled liquids because they are amorphous in nature, they have a tendency to flow. So, and then let me finish this. Then you have rubbers and plastics also can be a part of your amorphous solids. There is a possibility, because in that case, like you know, in that case you will actually have to create those pressure and temperature conditions to get the ordered arrangement. All you need to be very sure, because in this world where we can actually enter into quantum as well as the supramolecular chemistry, you can actually easily convert depending upon the types of atoms which are possessed in a particular system. In some cases it is not possible also, and in many cases it's generally possible, but the conditions are hard. They are also called pseudo solids because they're not actually the proper solids, in the sense that when you see glass as an example, glass is also called as a supercooled liquid. Why is it called a supercooled liquid? Because it has a tendency to flow. So many a times you must have seen many faculty members only citing this example, that when even my teacher did, that you will look, if you look at the window panes after a long time, so over a period of different seasons, you see that the bottom is thickened in comparison to the upper part, which is like thin. So that is why they are not the true solids, but if they have the tendency to flow, means you are comparing them to liquids. Because in solids, remember that in solids क्या होता है कि especially the crystalline solids, you have vacant sites which are occupied by atoms. ठीक है, जब atoms सारे occupy कर रहे हैं, they will not be able to vibrate freely because fixed positions है. So they will not be able to move rather, but they will only vibrate about the mean positions. So remember that for the solid state, all the solid state atoms, molecules, ions, radicals, whatever you talk about in solid state, that can only vibrate about its mean position. Okay, so now after talking about this, we can talk about other types of solids. This was based on the order. You have crystalline solids and amorphous solids. Just recap the differences on your own in your mind. Done? Really done?
Yes, ma'am.
No, some faces are like just looking like that. So now here we talk about the solids based on the intermolecular forces. Based on intermolecular forces. This we've done before. So based on intermolecular forces, we have different types of solids. So I'll quickly go through them again. One is like you can have molecular solids. ठीक है, molecular solids में ना generally वो वाले forces होते हैं, van der Waals forces, dipole forces. Van der Waals forces are what? You have London dispersion forces, dipole forces, dipole induced dipole forces, induced dipole forces. Or there is another class that is generally separated out from it, that is hydrogen bonded solids. So you can have molecular solids. So I'm not writing solids again and again. Otherwise my chart goes waste. Molecular, then you can have metallic solids, you can have ionic solids and covalent solids depending upon the kind of bonds that they possess. Now in molecular solids again, depending upon the kind of charges, depending upon the types of charges that each of the molecules possess, you have non-polar molecular solids, you have polar molecular solids, and you have hydrogen bonded molecular solids. Okay. Now in non-polar solids, you can, non-polar are the ones which have no charge separation. Polarity की बात हम सिर्फ तभी करते हैं whenever there is a charge separation. So if we talk about H2, there is no charge separation. We talk about a solid Cl2, there is no charge separation. So homonuclear diatomic. Homo means same. Diatomic means दो atoms का molecule. So homonuclear diatomic molecules generally form a part of non-polar solids. Yes, they can be. And they can be actually clubbed in a helium also can be there. Generally homonuclear diatomics to remember for examples. H2, Cl2, anything, any solid. Okay. Then for polar solids, wherever there is a charge separation. Charge separation, like why do you talk about? Solid sulfur dioxide, because sulfur's electronegativity is different from that of oxygen. So if you have any solid where there is an electronegativity difference, then you say that that's a polar molecular solid. So you have a solid sulfur dioxide, solid ammonia, solidified ammonia. It can be hydrogen bonding also, and then hydrogen bonding can be classified into polar molecular solids also. So you can talk about in both the cases here. Because in hydrogen bonded solids, you generally talk about hydrogen pairing up with any of the electronegative. Okay. So you have three type of solids which come under molecular solids. You have non-polar solids, you have a polar solids, then you have hydrogen bonded solids. Okay. Then in metallic solids, generally whenever we talk about a solid, remember that your metals there are considered to be positively charged species which are held together by a sea of electrons, and that sea is called Fermi sea. Alright. In metallic solids, your metal is considered to be a positive particle, positively charged particle, which is held together by a sea of electrons. And you have, see, whatever metals are what? Metals are generally, you have a nucleus which has a number of electrons around it. So it is believed that that metal is nothing but it's a positively charged entity which is surrounded by a sea of electrons which are there up as a part of the metal itself. कहीं बाहर से electrons नहीं आएंगे. Those electrons are a part of the metal itself. But it is believed that how metallic solids or the bond is formed. It's a metallic bond. And a metallic bond is nothing but where metals are considered to be positively charged particles which are held together by a sea of electrons called the Fermi sea. Fermi.
What is the sea?
Sea of electrons are generally electrons surrounded.
Okay.
Sea, but alright, so you have Fermi sea. Then we talk about ionic solids. Ionic solids are the ones which are held together by ionic bonds. Now in ionic bonds, they are directional solids. They are non-directional solids. Are you all sleeping now? Ionic solids are non-directional solids. Why? Because what are the ionic solids that you can talk about? Electronegative species can be fluorine, oxygen, etc. Then you have hydrogen bond, metallic, may you can talk about any metal, iron, copper, silver, gold, etc. Now
H2O2 have hydrogen bond. H2O2.
H2O2. If you talk about, yes, in H2O2 there should be a possibility hydrogen bond because you have an oxygen which is an electronegative species. Okay. Coming on to ionic solids now. Ionic solids, I am calling them non-directional. Let's take up the examples. You can have NaCl, MgO, zinc sulfide.
Now what does non-directional means?
Non-directional means जैसे if you have NaCl, ठीक है? तो Na is positive, Cl is negative. Now if I have Na and ionic bond form होगा तो तभी form होगा when Cl will come close to Na. अब Cl इधर से आए, इधर से आए, इधर से आए, कहीं से भी आए. Irrespective of the direction from which your Cl minus comes towards Na, it will form the ionic bond. It will experience the same electrostatic force. Electrostatic force is between two opposite charges, or you can talk about electrostatic force between any two charges. But when you are talking about ionic bond, you have an electronegative atom which is coming close towards an electropositive atom. So irrespective of the direction from which your other ion is approaching the other ion, I mean Cl minus is approaching Na, it will experience the same force from any direction. So that is why it is non-directional. Non-directional means irrespective of the direction from which your incoming an ion is approaching the cation, it will experience the same force from all the directions. So that is why your ionic solids are non-directional in nature. No. Ionic bonds are something in which one has to give the electron and the other has to accept the electron. It is, in fact, ionic bonds are defined as the bonds which are formed by complete transfer of
electrons.
So HCl will generally be classified into hydrogen bonded solids because of the possession that it has of hydrogen. graph I saw. Okay. Metallic solids are nothing but metals forming bonds with one another. Like for example, if I talk about copper, copper is forming bonds with other copper atoms, and copper is considered to be some kind of a positively charged species, because generally if you remember, metals are the ones which have the tendency to give electrons. So generally उनका positive charge character comes from there. तो मेटल को हम assume कर लेते हैं to be a positive charge which is held together by a sea of electrons, मतलब बाकी के जो electrons हैं. जैसे if I talk about simple sodium metal, ठीक है, sodium metal is what? You have 11 electrons, so that means 281. Let me just talk about the simple configuration. 281. So you have 10 electrons like that and 1 electron which is readily given to Cl, or sorry, which is readily available to be given. So Na has a tendency to become Na positive. So here your Na is considered to be a positively charged metal atom, metal ion, which is held together by a sea of electrons, are the other electrons which are there in the system. Okay. So in metallic solids, the metallic bond is generally considered to be a positively charged ion which is held together by a sea of electrons. Now what C? C is like generally a normal flooded kind of, we are talking about the ions to be present along with the electrons. Now because the electrons are more in number, you know that what will be majorly participating in that positive ion character? The valence shell. बाकी सब electrons तो बहुत सारे हैं, so that's a C. So metallic solids are the ones in which they are held together by a sea of electrons known as the Fermi sea. I've just given one name. And you don't have to get your mind boggled up, because if you can remember, good, otherwise MCQs में देखते ही याद आ जाएगा. So what you have next is covalent bonds. Now covalent solids are the ones which are held together by covalent bonds, and you know that covalent bonds are directional in nature, and that is by the virtue of covalent bonds are directional in nature because of hybridization. क्योंकि covalent bonds में हमेशा you talk about hybridization. Okay, if you talk about solid methane, that's a covalent solid. और methane में आपको पता है C is sp3 hybridized. So the angle always has to be maintained as 109 degree 28 minutes. So that orientation has to be proper. So you have SiC, carbon can be considered, then you can have SiO4, aluminium nitride, wherever the electronegativities are comparable. There you have a covalent bond formation. And you know covalent bonds are the ones which are formed by the sharing of electrons. Okay, then? Yes? The major difference between non-polar and covalent, you can consider them to be the same depending upon the intermolecular forces. Say if the intermolecular forces are simple London dispersion forces, like in case of helium that you stated, you will not talk about helium to be generally covalent. That will be a non-polar solid. If you talk about any other case, like for example H2N2 be considered to be them to be more non-polar in nature than covalent, they are like comparable. So here there can be a comparison of the properties, so that will be considered more as non-polar solids. Otherwise the bonding which is there in them is like sharing of electrons, so that's covalent. So not that prominent as in comparison to the comparable electronegativities. So it would not be wrong if you put them in that classification, but if a comparison between the two is concerned, then you have to give one weightage over the other. So no. Covalent net, in fact that's the name. These are known as covalent network solids. So a good classification can be that network solids, but if you actually put them in covalent network solids also, that would not be absolutely wrong, because the bonding which is holding the solid together is your covalent bond only. And what is a network? Which is something elaborate, spread over. Okay. Now there is another classification depending upon the types of atoms which are possessed by the solids. Please be very careful. Now I want all of you all to look up onto the board. Look up, so that at least we cover it up now and then we can elaborate it in the next class. We have talked about the classification of solids based on the order, that is crystalline and amorphous. Very simple. Then the next classification was based on the intermolecular forces. Let me tell you, there is a very nice table given in NCERT which talks about other characters like brittle, hard, soft. So there is no harm in going through it. It's an excellent table which summarizing the previous pages. So just take about 2-3 minutes time for me or for yourself to go through it and go through it. Then there is, depending upon the types of atoms which are there in solids, types of atoms, you can have either an A type of solids. अगर same type के atoms है ना, जैसे NaCl is an A type of a crystal. Why A type? Because there is a similarity in some kind of an atomization. But if you can also have an ABN type of a solid, where there is a drastic difference in the properties of A and B type of an atom. Clear with that? Now the next question comes, we are going to study A type only this year. A type of solids. A type are the ones. Now A का मतलब है कि we are only talking about the characters of the different atoms. If it possesses similar types of an atoms, we call it A type of a solid. If it possesses different types of atoms, we call it an ABN solid. Now, when we talk about the A type of solids, they can be, when you talk about A type of solids, you talk about simple cubic solid. Okay, first demarcation is done. Alright, here you have drastic difference between the cation and anion. Here you have almost the similar types. Before I move on to this, let me just introduce you to the terms crystal lattice. It is a 3D arrangement of points in space, simple a range of network which is like spreading over in 3-dimensional space. So you have crystal lattice is something which is like elaborately spread all over in all the 3 spatial dimensions. Now unit cell is the smallest representation of, or the smallest 3-dimensional representation of the crystal lattice, which when repeats itself gives you the entire lattice. Okay, the definition very important, all of you all must be knowing. तो unit cell में जितनी भी properties होती हैं, they are the ones which will be possessed by the entire crystal lattice. So that is the speciality, and this concept only has resulted in the nano world or the nanochemistry. But you know, nanoparticle, nanochemistry, I don't know if you've heard of it. So all this is because the properties which are possessed by the entire bulk is like classical, will be represented by the tiniest particle also, which is called the nanoparticle. Now here in solid state we are not entering the quantum world, but we are just talking about that in solid state a representation of points in space is your crystal lattice, and the smallest representation is given by your unit cell, which when repeats itself gives you the entire lattice. और जो properties इस unit cell में हैं, वही सारी properties will be possessed by your crystal lattice. Alright, so then we have, now let's talk about the unit cell in particular. Let's talk about the unit cells here. We talk about a simple cubic unit cell. Alright, simple cubic unit cell, that's also called the primitive cubic unit cell. What is the character like? If I am talking about, I have not shown the representation. This is your unit cell. If I put boxes here, there, everywhere, it becomes a lattice. Means you want me to put it? I'm bad at drawing, so I don't know whether I will be able to get it. Is it coming?
Yes.
Thank you. So if I put more on top, on the left, on the right, it becomes a lattice. But if I talk only about one particular part of it, which when repeats itself is giving you the lattice, that is your unit cell. Now when I talk about a simple cubic unit cell, that means my atoms according to simple cubic unit cell definition or the primitive cubic unit cell definition are only there at the corners. Now इधर कुछ चीजें you have to understand. If the atoms are there at the corners, this is the general diagram that you draw. Okay, इसका मतलब ये नहीं है that these atoms are held together by a stick or a bond. The bonds are not holding it like this. In fact, this is known as the point model. This is known as the point model, the one that you generally see in books. It is only for an understanding. This is known as a point model. In reality, your atoms are actually aligned in such a way that they are hard spheres touching each other. Maximum space occupy करते हैं unit cell का. Each of the solid state structures are so beautifully designed in nature that each of the atoms occupy the unit cell to the maximum possible size, right? So in this case what we have is, we have two atoms which are joined together. They will be touching the surface. ये समझ आ गया? So this is called the closed packed structure, जिसमें हमने actual चीज दिखाई है कि हमारे जो atoms हैं they are touching each other. But to understand we look at the point model. ठीक है, point model. और अब मैं समझा रही हूँ point model के through कि हमारा primitive unit cell by definition is the one in which the atoms are there all at the corners. ठीक है? And then the next that we talk about is face centered cubic unit cell, FCC you call it. Then you have a body centered cubic unit cell. FCC में apart from having atoms at the corners, you also have atoms at the faces. I want a different colored pen. So you will have atoms at the faces also. AA type से we means that the characteristics of the atoms are such that they are feasible to be joined together. कई बार ABN type में what you have is that the properties which are possessed by the anion are absolutely different than that of the cations. I will elaborate it further on as I proceed on. I'll just give you a hint of it, otherwise you don't get questions from ABN. नहीं, here what you talk about is you are talking about NaCl crystal. Okay, so NaCl crystal in itself is a unit cell. Remember, अगर मैं बात कर रही हूँ solid state structure की, I am saying NaCl crystal. So this doesn't mean that one unit cell will have only Na and the other unit cell will have Cl. No, one unit cell will be completely representing one NaCl unit. अब वो आधा 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 करके करे या जैसे भी करे, you getting the point? If I am talking about a crystal of solid carbon dioxide, so that means my one unit cell will be a complete representation of one CO2 unit. Is that clear to everyone? So remember that when I am talking about a unit cell, that is representing one molecule in totality. Fine. Now let me just come back to this. Simple cubic में you know they are at the corners. Face centered में they are there at the faces also of the cube. In body centered you have exactly at the center, right? And then you find out the number of atoms per unit cell based on it. Why do you have to talk about number of atoms per unit cell? जब अगर body simple primitive में you have 1, 2, 3, 4, 5, 6, 7, 8 atoms in totality. We talk about atoms, number of atoms per unit cell, because if I talk about here, I have to draw it at the back also. So if I talk about an atom here, at this corner say, alright, now this is being shared, or rather I should have taken it here. Okay, I take the atom here. Change of position. No controversies with anyone. So you have the atom here. Now this atom is being shared by एक अगर इसको मैं main मानूं for checking up, it is being shared by 1, and then you have in the front also 2, and then you have at the back also 3, and then in fact let's concentrate on just this corner. This corner is being shared at present by 4 unit cells here and 4 exactly in the front. Okay, otherwise you have top, bottom, left, right everywhere. So this corner is being shared by 1 unit cell, 2 unit cell, 3 unit cell, 4 unit cell and 4 in the front. ठीक है? Can you see them? So this corner is being shared by 8. So if you divide each of the parts equally, so every corner will get 1/8, and the total number of corners are 8. So you will have 1 atom per unit cell. Similarly for the face centered, you have how? You have 1 by 8 into 8, that is there. Then you have one atom exactly in the center of the wall of the cube. Alright, so that is half shared in one one unit cell and the other half is in the other unit cell. So the contribution will be half per unit cell at each face into the total number of faces, that is 6, and that will be total 4 atoms per unit cell. And body centered mein, it's very easy. You have atoms, yes, 2. You have atoms at the corners. So corner wale again will be 1 by 8th contribution into 8. So corner wala is absolutely clear, 1 by 8 into 8. Plus there is one atom absolutely at the center. So that center one will have a 1 full contribution. So that will be 1 by 8 into 8 plus 1. So that is 2 atoms per unit cell. Okay, then you have end-centered unit cells. Let me just give you now. You know how to find out the number of atoms per unit cell? All of you. If anyone has any doubts, I'll take it up again in the next class to explain. Then I'll get models or probably use pens and sticks to explain the number of atoms. Or I'll try to improve my representation on board. Now I am giving you one diagram for a HCP unit cell. Alright, ready all of you all? Find out the total number of atoms per unit cell in this case. I have a hexagon, okay, and a hexagon below. Looks like a hexagon. Please join the lines. Okay, looks like a hexagon on the top and the hexagon at the bottom. Clear? Now I have atoms at each corner. So this is the structure that I am giving you. So atoms at each corner. Then 3 atoms at the corners. Position understood? Now 3 atoms are wholly within. 3 atoms are wholly within the system. And then you have one at the top and the other at the base. 2 at the topmost face and, sorry, 1 at the topmost face and 1 at the bottommost face. Now tell me the total number of atoms which are possessed by this unit cell. Okay, work it out. You can't work it in the air. Dekho, 3 atoms, I'll help you out because time is almost up. There are 3 atoms wholly within. उनका total contribution will be 3. क्योंकि वो तो अंदर है, वो तो share ही नहीं होंगे. If you have atoms wholly within, they will not get shared at all. Now, the topmost is easy because वो face के center में है. तो the contribution will be half into कितने faces में है? 2 faces में है. तो 2. So this is clear. Now we are left only with the corner ones. Now for the corner, you have, let's concentrate on this corner. Alright, you will have one hexagon here, and you will have another hexagon here. So there are 1, 2, 3 hexagon here, जो इस point पे share करें और 3 इसके ऊपर. So how many? So the contribution will go to 1/6 per corner. ठीक है? समझ में आया? एक corner पे atom है, that corner is being shared with 3 unit cells here. 3 hexagon ही बनाने थे ना, तो 3 hexagon इधर और 3 hexagon इसके ऊपर. So the contribution per unit cell will be 1/6 because it's being shared by 6 unit cells into the total number of corners. That's 12. Into, you have how many corners now? 12. So that will be 1 and then you have 2. So 2 plus 1 plus 3. So 6. Alright. So that way any representation of the unit cell which is given can help you find out the total number of atoms per unit cell. Alright. And from here we'll proceed on in the next class. One question, how many A-type lattices are there? 4? No. There are 14 A-type lattices which are known as the Bravais lattices. S is generally silent, but Bravais, whatever you want, you can call it. They are the 14 Bravais lattices. So A-type lattices are not restricted to these 4. We study these 4 only because of one reason. Periodic table, all of you all know. Nearly 80% of the elements which are present in periodic table exist in either of these 4 forms. SCC, FCC, BCC or HCP. ठीक है, क्योंकि 80% of the elements exist in either of these four forms, so these have been picked for your study so that you do what is more important in nature than doing each one. And you know, otherwise there are how many? 14 Bravais lattices. They are given in your also, and we shall be doing that in the next class. All right, so do it properly then. Thank you.